EC 111 lecture 14, set 4. I will continue with describing the final project and talking about some expected range of results for the project. So now, this is, of course, the numbers may not make much sense to you at this point because you have not probably implemented the design, but this is something for you as a reference. So once you do the design, you can come back and see what kind of numbers you've got. And if the numbers are completely off, then you know that you could do better than that. So this is just kind of to guide you on your optimization. And, as, I mentioned earlier, we have a sequential and parallel implementation. The sequential implementation, we're trying to optimize area delay product. In the parallel implementation, they really only care about the timing of the design. And, we need to use one SHA-256 unit to enumerate 16 nonces. But then, in the targeting the delay, we're going to create 16 SHA-256 units and then use each of these units twice, or actually like 3 times for each of the nonces to get to the results. Now, this is as I mentioned, this is if you're getting a parallel area delay optimization, this is kind of the area delay that you're seeing. This is like kind of from a former class, the median of the class. I mean, the reason I didn't put average is because, some people have, not been able to do any optimization. So the average may be kind of very skewed. The median shows like a good range of the results people have gotten. As you may know, that a mean is very, very sensitive to the outliers. And the delay only obviously is going to use a lot more resources, a lot more researchers for if you're doing delay only, because we're basically doing a lot of parallelism. The area is obviously going to be a lot larger than when we're doing area delay product, but the number of cycles, as you see, is about 10 times less. So we're going to pay kind of more than 10 times penalty in terms of the area, but we're going to improve the number of cycles by about 10 times. And, the delay is kind of a function of that. As you see here, the Fmaxes are kind of in the same range. As you see, here the maximal frequency is slightly higher, but not by much from this. And the area delay is actually optimized for this, but the median results people got was this, and this is the possible. This is possible to get on the parallel implementation, but this is the median of what people have got. So people didn't do all the possible optimization. As you see, the median of the class hasn't done all the possible optimization in the in the parallel case. So the median, for example, for the frequency is much lower than what is achievable, but still people have been able to get like a good number of cycles. Okay, so just like any other thing, like if I ask you to paint a flower for me, like I will have probably as many students as there are in the class, or as many groups there are in the class, different instantiations of a kind of flower that I have put here for you to paint. Now, it is the same here. There are several possible implementations. There's no single right way. The goal is to get you as close as possible to the best possible. But of course, we understand that this may not be, exactly doable. But, if you're too off from the median, then you know that you've done something wrong. So make sure that you're not too much off from that number. And in the final state machine code, you have to use combined always blocks for sequential combinational logic using non-blocking assignments. And the thing is, also, in this project, in any project that you do, the most important thing you could do if you're trying to help yourself both to learn and also to have clarity and have usable design, you need to make sure that your code is very readable. And if you're putting too many if then else's in your code, then it is hard to read. Try to simplify the code, to the say case statement. Don't try to have too many nested things, because sometimes when you're writing you may have this thought and just keep nesting things. If this happens, that happens. If this happens, that happens. But that actually impacts readability. And remember that always minimizing the number of states is not necessarily good if you're adding too many if then else. So remember that at the end of the day, the compiler is doing some optimization on the state numbers, so which we don't have a control on, and it's pretty okay in that respect. So don't try to manually try to influence and optimize it. The code should be as readable as possible. Try to add comments before each block of code that explains what is it trying to achieve, so you could have an easier time debug it. Very often I have seen people coming, with the code, to the TA session, or even to me, and they ask me to debug their code. But this is something that is completely out of question, in particular if I can't even read the code. So if you have a more readable code, it's much easier to debug. You could actually probably ask some questions from the TA on kind of some generic things. Detailed debugging of the codes is something that is not within the scope, of course, because you're expected to do the debugging at that level yourself. But generic guidelines and talking about, like, is this method correct, or do you think this is this could work, that is definitely much more easier to explain if you have a more readable code that is commented all over. Now, the other advice that I always have to people who are trying these designs is that you always have to try to go smaller, basically divide and conquer. You try to do a smaller, say, number of nonces. So you kind of start like the parameters to in the test bench to be smaller, and try to look at the output. And then if that's kind of working, then try to expand it to more number of nonces. And then here, for example, in the example I'm putting here, we could put the nums as a parameter, and we could try to change that parameter to have a smaller design running and testing it, as opposed to doing all the 16 nonces all the time, and then seeing some bugs in that is one gets propagated to all of them. That's not gonna work. For the submission, this is kind of the logistics and format, but we have a particular way of combining the files with names, and this is because we have seen in the past that grading can become difficult if we don't have all this all this information. So please make sure that you follow these guidelines, and in addition to doing the project, you have a detailed explanation of the summary of the results as we expect, the report template which is shared, which will be shared with you, and the kind of split your design into different .system Verilog files. So if you're doing one for minimum area delay and one for minimum delay, then have two files. You may want to try different implementation and even share it with us. If that's the case, then also put all of those into these SV files. And have different transcripts for them. You know, this is kind of easily to explain, like, you know, once you go through the description of the final project and see how these reports are done. So we want, like, you know, one report, you know, for the minimum area delay, kind of one report for the the min delay, and kind of the same is true for the other parts that you're doing. And the template for the final summary is also given. Here is just kind of an example. You know, we want this, you know, the names here, the student IDs, the contact, you know, the what compiler settings did you use, and, you know, I'll be briefly talking about that. That's, you know, more importantly, the number of LUTs, which is kind of, if you're in the same team, of course, you know, the results you're getting is similar. But, you know, if you have more files than one, then you could actually add those here and, you know, talk about that. You need to make, you know, if you're alone, of course, you only do one row. The kind of the calculation fields are given in this file. So, you know, you just kind of go through the results from the compiled version, and then you read what you have in terms of the LUTs, register area, Fmax, and so on, and you report them here. Make sure that you use this this device when you're compiling. So this is available in the you know, in the Intel Altera pack. You know, the Fmax is model that you need to use is this one, and then you know, you use the total number of cycles when you're doing that. And then you know, the minimum area delay design, we're going to call this #1, and the minimum delay, we're going to call it #2. If you have more names, more files, you just add them and rename them as needed. In the next couple of sets, we're going to talk about more optimizations that can be done so you have a better implementation of the design. So we could get those numbers down to the best possible that we have seen, you know, from people designing this before. Stay tuned for that.